Yeah. Welcome to Ryan Lafler's Master Thesis Defense. His parents, grandparents are here. That's really nice. And thank you for attending from Zoom. Well, first of all, we are all impressed with Ryan's work. We all know that. And then he has done so much work. I'll give you a few indices to see how much work he has done. And in terms of number of lines of code, I believe just relevant to the thesis research, that probably is over 30,000 lines already. And then other one will be in other indexes, the volume of work, the products he produced. That is normally that will be enough for 3 kind of regular thesis. So he works in the lab, and then I thought sometimes I got the impression he doesn't sleep. But anyhow, so welcome. And then so next 20-30 minutes, Ryan going to make a presentation, and then committee will have questions. And not only committee, but audience can ask questions, and eventually committee will ask questions, and then we will have assessment.
That sounds good. All right. Well, thank you for that introduction, Sam. Let me get this in the PowerPoint. And of course, I'd like to thank all of my committee members and my program coordinator, Dr. So. He can't be here. He's actually on sabbatical right now, but he helped facilitate and orchestrate this thesis. So I really appreciate his help here. The title of my thesis is Video Remastering, Programmatic Methods for Frame Interpolation, Resolution Upsampling, and Frame Enhancements. So there are several components to this, but to boil it all down, we want to take an existing video and increase its quality, boost its frame rate, and also make some nice enhancements with it. It also comes with metrics to measure how sizable the improvements were. So you can quantitatively and you can visually see the improvements. So we'll go through this. And everything should be screen sharing on the Zoom as well. I don't recommend you look at the PowerPoint from the video camera. So hopefully that's screen sharing on Zoom. Just to go over my thesis committee members, Dr. Samuel Shen, he introduced me. He's been a great inspiration for my work here at San Diego State. We've done a lot of research together, collaborated on a lot of projects, so I'm grateful for his mentorship. Also, Dr. Joey Lin, he is on the Zoom right now. I appreciate his help. Dr. Bailey, Dr. Duncan, I've worked with them. I've learned from them from many classes, so it's great to have their help on this thesis. All right, let's talk about the introduction and also the purpose of this thesis, why I particularly chose this, what the problem I tried to address with it was. So I wanted to develop a customizable Python program that was able to accept any video, usually of MP4 format, and upsample the resolution, increase the frame rate, and produce a remastered video from it. Also in the program, instead of just using for loops, which take one line of code at a time, I wanted to scale the program so that if you had additional resources, more CPUs, cloud computing where you could purchase more resources, the program will be able to scale with it, so it will become more efficient. And that's where parallel processing comes into play. There could have been another method used as well. Instead of doing it algorithmically, we could have made a deep learning model. I chose not to go the deep learning route because this was about producing baseline results. So given the results that we see from this thesis, you can make a decision as to whether do you want to pursue a deep learning model, or are you satisfied with the results that came out from the algorithms? And that's what the metrics are going to help us interpret. So we'll talk about some preliminaries, some of the Python packages that were used, also just setting up some of the math notation. I promise it's not too formula heavy. That's all in the thesis. I just want to talk about the broad concepts in this PowerPoint. So some of the program dependencies and the major libraries I used was the OpenCV, Open Computer Vision Library in Python. It's a massive repository for a lot of kernel convolutions, right? Things where you can change images, adjust videos. It has built-in functions that kind of speed up the process rather than just coding it all in Python, making your own functions. Another one is the Python imaging library. This was really helpful when we're dealing with large images, so 4K images, high quality images. This library helped in manipulating those big image data. The MoviePy library created the remastered video in Python, so you don't have to go to a third-party software to stitch the frames together and all that. It's all done in the Python program. TensorFlow is a big one for a lot of algebraic manipulations. So when we're looking at linear algebra, the matrix algebra, it was all done through TensorFlow. And that's a pretty powerful library that allows for deep learning, neural networking, but we just utilized it for the algorithms that it has inside of it. Same with the NumPy library. It's an array-based library for handling a lot of matrix data. The Pathos library is where the parallel processing occurs, and it is a high-level library that really simplifies the parallel processing in Python. It's one line of code, you can customize it, and you can turn any function into a parallel processing function using this library. The Pandas library spits out a data frame, so it's kind of like the R equivalent of a data frame, but for Python. The Matplotlib library was for visualizations. And these two down here, it kind of simplifies some complicated for loops and iterative processes. And it also allows me to store things in external directories. So instead of keeping everything in the Python session, we're going to export it to external directories, maybe in the cloud, maybe on an SSD drive, just to get it outside of Python and into a directory. So for parallel processing, the whole point of it is you want to bypass the for loop. Now, the for loop is great if you want to start there, but if you want to scale a process and put it across multiple CPUs, parallel processing is the best way to go. Instead of focusing on just one task at a time, well, if you have 4 CPUs, you can use each CPU on your computer to run a task. So it's going to scale the process and distribute it across CPUs. That's going to give us a significant performance increase. And it's also bypassing something called Python's global interpreter lock. And essentially that locks Python in to running one line at a time, so sequentially. And one thing that has to occur for parallel processing is it needs to serialize objects. The best way I can interpret that or explain that is serialization is where you take a Python dictionary, for instance, and you turn it into a JSON file. So you turn something that's Python native into a universal format that's understood. So it needs to be serializable and also deserializable to turn it back into that Python object. So the Pathos module does all this by default. And since it does it by default, it really is, it simplifies the process of parallel computing. The next one is mathematically expressing frames as arrays. So in a video, we have a sequence of frames of a specific resolution that play at a specified frame rate. So the frame, which represents an image, I pretty much use it synonymously in this presentation, is a 3D array. And it has 3 matrices inside of it, a red, a green, and a blue color matrix. Now, what those color matrices indicate is that they store values between 0 and 255. You can also normalize them to be between 0 and 1. And what that tells you is how intense that particular color is. So if you have a color that's 255 in red on the red matrix, and then 0 on the blue, 0 on the green, you're going to get a pure red color. So you can use those values to achieve any color on the color spectrum through an RGB array. And for the duration of this thesis, the way we're going to express arrays is that they have m rows, n columns, and 3 color channels, just to generalize it to any video we want to look at. When it comes to the metrics we'll be talking about to measure the quality increase from the remastering process, there are a few things that we can look at. One of them is the structural similarity of an image, how similar 2 images are. And there are 2 metrics for that: structural similarity index measurement, and also its multi-scale equivalent. And we'll take a look at those 2. For measuring image quality, we'll take a look at the PSNR, the peak signal to noise ratio. And it tells us how good or how bad in terms of quality the remastered frame is to the original frame. And then the last one is pretty rudimentary, it's basic, but it's an input to the PSNR, and it is the overall average pixel difference. It's the root mean squared error. It's pretty common in regression, and it has a nice application for image processing. So we'll talk about the structural similarity index measurement first. It takes into account three components: the luminosity of two images, and that's the average pixel intensity; the contrast, which is essentially the covariance of pixel intensities between two frames, so the shared variance; and also the structure of an image. Now, the structure and contrast are two closely related things, but the structure is kind of like the correlation between two images, how alike they are, how similar they are. So by looking at luminosity, contrast, and structure, using moving windows and sliding across every single pixel of these two frames, we can calculate a structural similarity value. Now it puts these structural similarity values for every single pixel in the array. That's not very informative. We want a global measure. So what we're going to do is take the average of these local sim values and calculate a global average from it. So we get one scalar, one value to measure how similar they are. And they have a nice interpretation. If we have a value that's close to -1, the two images are negatively similar. It's kind of like a checkerboarding effect in a correlation. If we get a value that's close to 0, the two images are not at all similar. So could be due that they are completely different images. There's some distortion, but if it's close to 0, it tells us that there's a problem with the images. And if it's close to 1, that's ideal because the two images are structurally similar. It's like a positive correlation. The multi-scale structural similarity kind of extends what we talk about, or what we talked about, and instead of looking at it from one resolution, now we're looking at it from different resolutions. So what it does is it takes an image and it downsamples it to a worse quality image, and it computes the same metric for each downsampled image. And what that does is you can look at it from different perspectives. So it becomes blockier, more pixelated as you downsample. And that allows us to look at the similarity from different perspectives. That's what the multi-scale similarity measures. And it has the same interpretation as the structural similarity. So it's measured between -1 and +1 with the same interpretation. The peak signal to noise ratio, the PSNR, has a nice interpretation to it. It's measured in decibels, and it is measured on the logarithmic scale. So what we do is we take two images, an image of high quality and the same image of low quality, and we can calculate how different they are in terms of their quality. So what it looks for is distortion, noise, artifacts, compression problems. These are all typical things we use PSNR to measure. And what we want to see is a high PSNR value. There is no upper bound, but the higher the better. And it has a lower bound, obviously. It can't be below 0. But the component to the PSNR from this formula right here is the root mean squared error. And that's the noise of our images, how noisy they are. We'll talk about that next. Actually, we'll go through more interpretations of PSNR. So if we have a PSNR value that's less than 20 decibel, it tells us the original image is of extremely low quality. And that's a bad result. If we get something between 20 decibels and 30 decibels, the original image is going to look like the upsampled image, but there's going to be some noise that may be visible, may not be visible. Again, when you're using these metrics and comparing it visually, they're not going to line up perfectly, but it'll give us a frame of reference to look for. Because visually assessing how good an image is subjective, but these at least try to quantify it. And if we have a PSNR value that's greater than 30 decibels, it tells us that the original image is visually indistinguishable from the upsampled image. So we obviously want to try to get our PSNR values above 30 decibels. Now the root mean squared error, what this does is it takes the average difference between two image arrays. And once you do that, or the average squared difference, I should say, and you take the square root of that, that's how you can get the root mean squared error. And this is just measuring the noise between two images, so how different they are. And it's a nice, simple global measure to see how different two images are on average. All right. When it comes to bootstrapping, we can use these metrics and bootstrap from them to glean some statistical inference from it. So what we do is we assume that the frames extracted from a video clip are the entire population of frames. And we take a stratified random sample of those frames. Why stratified? Because I want to make sure I hit frames from each part of the video, from the beginning, the middle, and the end, because I want to measure that represents the population. And then from that stratified random sample, we calculate the metrics we talked about: structural similarity, PSNR, root mean squared error. And then we sample with replacement on those metrics. This is the bootstrapping part. 1,000 times to generate point estimates, standard errors, and confidence intervals for the median and standard deviation estimates. Now I chose median because it is robust to outliers, and I chose standard deviation because it isn't. So it'll give us a nice measure of how those outliers are impacting our measures of center and measures of spread. And here, just talking about that again, we're using the median and the standard deviation. And by default, we're using 95% confidence intervals. These are percentile based. So what we do is we look at the 97.5th percentile and the 2.5th percentile of our bootstrap distributions, and that creates our lower and upper bounds for the confidence interval. Switching gears here, now going more towards the Python program itself, the image database. And I know it's a little bit difficult to see in here, but what it does is it creates a directory of folders and subfolders where it stores the metrics, the frames, the clips, and all that data in an external directory. And this just shows the flow of it. When it comes to naming frames, we want to preserve their sequence in the video. So I came up with a naming convention. If we're looking at the first frame, for instance, of a video, we're going to call that 000, and it takes up to 1 million frames. So depending on its sequence in the video, this number right here will change so that we can just call it back into Python and restructure it like it originally was. So we try to preserve the structure of the video using these naming conventions. Next, we'll take a look at frame interpolation methods. We just have a few examples here. So these are a sequence of frames and the observed halfway frames. So in the first column, that's the first frame that you see. The second column is the halfway frame. The third column is the next observed frame. So what we're going to do here is we're going to use the first column and the third column to interpolate the middle column. And we're going to compare our interpolation estimates to those true frames using the metrics we talked about. The first one we'll discuss is element-wise averaging. So what we do is we take the average of those two observed frames and we get an estimate from it. On the left side, that's the true frame. On the right side, this is the interpolated frame. So you can see where there are differences between the true and the interpolated frame. Mostly when it comes to average interpolation, it performs pretty well. When you're taking the average of every pixel, it can be computationally inefficient. There's another method we'll talk about that kind of bypasses that, but this is a decent tool for frame interpolation.
Can you clarify what a true frame is? Were there
Oh, yeah.
actually 3 frames originally, and that was the
Yes, exactly.
Pretended, so you did an experiment where you knew the answer.
Yep.
Yeah, exactly.
Yeah. So this constituted the validation test.
That's always a good idea.
Yeah. Yeah, since we had access to the data, we just took that true frame, that's like the middle frame that is in the video, and then we compared it to the interpolated frame that is what we estimated using this algorithm. Okay. Yeah. So when it comes to the metrics, here we have it for on the rows, we're looking at each video that we visually saw, and on the columns, we're looking at the types of metrics. So structural similarity for the first video was exceptionally high. It had a structural similarity value that was close to 1. When we talked about that, we wanted to see values that were close to 1 because it implied the two frames were strongly alike. Multi-scale structural similarity is even stronger when we look at it from different resolutions. So it's even more likely. The peak signal to noise ratio, about 26 decibels rounding up. That's a great value. It tells us that the interpolated frame and the observed frame are of nearly indistinguishable quality. So it's a good estimate. And then root mean squared error, not too much meaning here, except to just compare them to one another. For the second example, the root mean squared error was pretty high. Let's take a look at why. If you see, they look pretty different, right? Well, that's because averaging interpolation takes the average of those two frames. So it blends the first frame with the next observed frame. And you can see that that process is reflected in the interpolated frame, which looks pretty different from what we actually observed in the video. So the structure.
Oh, you're not there yet. I was gonna say the other one is a PlayStation.
Yeah. Yeah.
Number.
So I wanted to try to incorporate in these metrics things from television shows, movies, video games, and also historical footage. That's the last example. So I just wanted to give you different applications of where this could be used. But yeah, looking at the structural similarity for this, it was not great. So definitely average interpolation failed on the second video. For the video game cutscene, the similarity was a little bit higher. We're close to 20 decibels when it comes to PSNR, which means we're approaching a decent quality, but we're not quite there yet. And for the historical footage, well, let's take a look at that one again. We have something of different images. There's a car here in the interpolated frame that doesn't exist in the true frame. So even though the estimated image is going to make the video flow better, right? We're doubling its frame rate. It's not going to be an exact replica of what we observed. So this is what comes with the interpolation process. I would actually recommend a deep learning model to try and improve on these baseline results. But again, this makes a good starting point. The next one we'll talk about is singular value decomposition. And there's actually two methods for doing this. It's going along the rows and going along the columns. It's a pretty complicated formula if you've never seen it before. Well, what this does is it decomposes one of the frames, finds a relationship to the first observed frame and the next observed frame. And then from that relationship, it tries to make an interpolated value. This was actually the first algorithm I tried when I made the thesis. And as you can see, when we're going along the rows, we get an image that looks pretty distorted, especially in the second image. It's kind of reminiscent to what you would experience by looking at something printing out from a dirty printer, right? You have these horizontal lines that tend to just mess up the paper. It's the same effect here. And why? We're going along the rows. If we look at the dimensions, which are in parentheses for each video, we only have 720 rows here versus 1,280 columns. There's less rows in each of these examples than there are columns. So we're losing out on information. There's another approach where we can capture more information. Here are the metrics for this. As you can see, pretty poor quality, especially for that second example. Where we can move along the columns instead of the rows. And we try to use more information to preserve that relationship. And here you can see we lose that vertical line effect when we use that information in the columns. And the images are closer to what we saw with average interpolation. So these methods are lining up. They're producing roughly equivalent results. Just depends, in this case, if you have a lot less rows than columns, you want to use columns. If you have a lot more rows than columns, like if you're recording something vertically on your phone, you'd want to use the row approach because you have more rows vertically.
Is it just coincidence that the Spider-Man movie 21 years ago, the technology was not as up to par, and that's why the interpolation is not as...
That's a good point, right? So when it comes to historical footage, it depends on the original quality of the video. What we try to do, and there's a frame enhancement process after this we'll talk about, but depending on the video you insert into it, if it has a lot of tearing in it, artifacts that's from historical footage, it's going to be reflected in the interpolation process. So if we're looking at videos that came from a long time ago, the noise in those videos and the way that they were recorded is going to be reflected in this process. Now, there are some ways that we can minimize that and try to mask it. But right now, when it comes to just interpolating it, that problem is going to persist.
Wasn't that one the shark type one though anyway, right? You
Yes.
specifically chosen that. 'Cause
Exactly. This example right here, the Spider-Man 2002 movie, that was what we call an abrupt scene cut. So looking at the original frames again, we had one frame that was completely different from the next frame. So when you have these really different frames, you're going to get a result that tries to blend these two extremely different frames together. And that's why it doesn't, visually seem up to par as the first example, which is the two frames are really blank. And that's why the first example was really good compared to these other ones, because they're more abrupt scene changes.
So you may not be able to use the Zapruder film from 1963 in the assassination of Kennedy to improve.
True. Yeah, I would not use that to generate historically accurate results or try to find anything from that. This is just something where you can smooth it out. Now, who knows, maybe with deep learning, a model that can try to learn and optimize itself over time, you could use something like that. But for generating baseline results with that, I would be very careful interpreting things.
Your metrics would fail, right?
The metrics would fail, yeah. Especially when it comes to PSNR for old videos that are of bad quality, it would really fail in that case. And then finally, the last frame interpolation method is linear interpolation. So there's actually a setting on most televisions called motion blur reduction that kind of mimics this effect. So what it does is it takes the first frame and the second frame, takes the difference between them, and then after that, it adds that difference frame to the first frame to produce everything on the right column. So you can see that it's very similar to average interpolation, but the results are better. The performance is more efficient because now we're not averaging things, we're just taking the difference, and that really speeds things up in Python. Looking at the metrics, the first frame did exceptionally well, or the first video did exceptionally well. Second video we saw, the third video we saw improvements. So for the video game, the historical footage, again, it was pretty close to average interpolation. Now, what I found interesting when I did this is that this actually performed worse for structural similarity than taking the singular value decomposition. Now, visually, I don't think that's the case, because to me, we're not seeing those vertical lines anymore. But this kind of brings up the debate between how do you interpret things quantitatively versus visually. So you have to be careful with the quantitative metrics. They can only take you so far when it comes to interpreting things. But these are the results from that linear interpolation. So just to go over this really quickly, linear interpolation was the best, most optimal approach. Singular value decomposition interpolation, SVD, can produce equivalent results when the number of rows and columns are roughly the same. And if there's a huge disparity between rows and columns, which there often is in videos, SVD interpolation may not be the approach to go. But just know that these methods will produce roughly equivalent results. They spit out the same image. There just may be issues with quality, with noise, artifacts that may destroy the interpolated image. But for the remainder of this thesis, we'll be using linear interpolation to produce baseline results. The next component is the resolution upsampling phase. And it also has a frame enhancement process. So we'll be talking about Lanczos resolution upsampling. That's a very nice spatial way of interpolating for these missing pixel values to increase the resolution. And also we'll talk about additional convolutions to try to enhance these images, make them sharper, smooth out any noise, try to mask the noise. So we'll talk about kernels for that.
That's machine learning.
Most kernels are used in machine learning. The ones in this case are not used for machine learning. They're just a standard set of kernels that move over every pixel in an image, and they change the value of each pixel given nearby pixels. That's the whole point of a kernel. We'll talk more about that. So what this does, and this is the process for it. is we first push it through the Lanczos-3 upsampling algorithm. After it goes through that algorithm, we also put more image enhancements on it. So we adjust the brightness, the contrast, the gamma, the sharpness of an image. And after that's done, then we run these additional convolutions. There are 3 convolutions that we use actually for a Gaussian blur, a median blur, bilateral filtering, and unsharp masking. We'll talk about what each one of these does. Unsharp masking is an edge preserving filter. So what it does is it tries to identify edges in an image and tries to sharpen only the edges. So what's an edge? Well, it's something that has a rather distinct change in pixel values. So if we look at the edge of a building, we're going to look at the perimeter of a building. Now that perimeter is going to look different than the things around it because that's an edge. So it's going to identify these edges and only sharpen the edges, leaving everything else untouched. After we do that, we put it through a bilateral filter, and that has a way of reducing the noise or the over sharpening that could occur from unsharp masking. So it's a way to smooth over the noise of an image. And it uses a Gaussian blur, actually 2 of them, to try and do that. And then finally, the last stage is a median blur. And what that does, it's simple, is it looks at for every pixel value. It moves a 3x3 window across every pixel, and based on the pixels that are captured in that area, it takes the median of it. So it's a simple, very rudimentary measure for smoothing an image. And after this process, that is how we get our upsample frame. So here's just a simple kernel convolution so you know what I'm talking about. Let's say we have a 3x4 matrix that contains our pixel values, and we're going to run a 3x3 kernel on every pixel value in this matrix. So what this process looks like is when we start on this first pixel, C11, we're going to center our kernel on that pixel. Now the kernel is going to go outside the boundary of our image, and that's fine, because we're going to pad those numbers outside of it with zeros. It's called constant value padding. And what it does is it takes the original pixels, multiplies them with the weights, as you can see here, and when we flatten it to a vector, just to simplify things, we add up all of the weights multiplied by the pixels to change that one value. And the process is repeated for every single pixel in that array. So it can be an intensive process, but when we talked about what OpenCV does, Open Computer Vision, this is what it does best. I think it's built or compiled in Fortran, so it has a speedy way of doing it in Python.
Does this also handle with the parallel processing?
Yes, this is built in with the parallel processing. So for resolution upsampling, when we're talking about that, we're using the existing pixels of an image to achieve a higher quality. So let's say that we have an HD 1080p image. We can use resolution upsampling to get a 4K image out of that just by using the existing pixels. There are many algorithms that exist. One of them is nearest neighbor resizing. Another one is bicubic resizing. But from my research, what I found is that resolution upsampling with the Lanczos kernel is the best. And it doesn't use a Fourier transform or anything like that, so it keeps it in the spatial dimension. And what it does is it runs a convolution over the original pixel values, and it estimates every single pixel value that is between the observed ones. So it tries to estimate those unobserved pixel values. It also has a choice of hyperparameter that we can use. We're going to use the Lanczos 3 kernel. It's the best compromise candidate, but depending on your choice of that parameter, you can change the influence of nearby pixels. So do you want to have pixels that are far away influencing the interpolation, or do you want to keep it close? We'll take a look at what that looks like. When it comes to the Lanczos kernel, it is rooted in the sync function. And essentially what that is you take the sine of x and you divide it by x. And that's how you get the sync function. We're going to use the normalized sync function because it has an area of 1. And it also converges to 0 a lot faster than the unnormalized version. And how do you get the normalized sync function? You take the sine of pi of x and you divide it by pi of x. And that's how you can normalize it. And here's the formula right here. So it's kind of like a piecewise function. It is not defined for one, but we'll make it defined for when x equals 0. It's going to output a value of 1. And that normalizes it to have an area of 1 under the curve. The reconstruction kernel, which is where we get our weights from, is where you take that sinc function and you multiply it by another sinc function. It's called a window function. And that's what that sinc pi of x divided by a is. When we're looking at these different images for values of a, the kernel changes, right? So as a gets bigger, the parameter, the influence of faraway pixels increases as well. You can see that the curve kind of stretches at that point. So we have non-zero outputs farther away from the central pixel. And it can have positive and negative weights. This is just for getting weights for a current. Calculating interpolated pixels. So when we're looking at a color matrix, it's marked by an x-axis and a y-axis. It's a matrix. So we want to find the position for the unobserved pixel at a certain position. Well, this is the formula for doing it. We take our reconstruction kernel, we multiply it by the observed pixels. So again, this is a convolution. We have our weights multiplied by our original pixel values, and we sum them all together. And what that does is it gets us an estimated value in between the observed pixels. And since these convolutions run independently on each color matrix, so each red, green, and blue array, we can simplify this reconstruction kernel to be a product rather than a joint kernel. And that massively simplifies the process. And then in this one, generating validation data sets for metric evaluation. So what we're doing here is we are using our sample of frames to generate some validation data sets. So this is how we get our bootstrap estimates and all of that stuff. For frame interpolation, we are going to take a random sample of frames. We're first going to split the video into the beginning, middle, and end parts. And then we're going to take a simple random sample inside each partition or strap. So let's say that we have a sequence of frames, xi, xi plus 1, and xi plus 2. Well, the way we generate our validation data sets or our estimates is we take xi and xi plus 2, and we calculate xi plus 1. So we know what it really is, but now we also have an estimate for it. And we can compare those two things. And then once we have our metrics for structural similarity, multi-scale structural similarity, PSNR, RMSE, we're going to use bootstrapping to estimate 1,000 median and standard deviation estimates for these metrics. And that will allow us to create confidence intervals to see what the true median, the true standard deviation estimates truly are. For resolution upsampling, the process doesn't change much. We're still using the existing data, taking the stratified random sample, and we're bootstrapping to produce confidence intervals. We'll just take a look at a few results. So for this one, this is after the resolution upsampling process. This is the visual component.
2012.
Yeah. So this one's
I'm still 2002.
And you can see here in the original frames that they are darker, a little duller, more blurry. Well, what we did with the upsampling process is using digital unsharp masking, we enhanced the color depth. So we brought the colors out more. We made the edges sharper. And you can see here that the edges are more well-defined. The background is more well-defined. And we also reduced the noise in the original image. So that's what the resolution upsampling process does. The interpolation metrics for it. When we look at each metric for structural similarity, the true median structural similarity value is going to be somewhere between 0.69 and 0.7. So we're 95% confident about that. And I'd say that that is a moderately strong similarity value. The multi-scale structural similarity has a little bit of a wider confidence interval. So when we look at that from different resolutions, we have less certainty. that the true median value is going to be of moderate quality. For the peak signal to noise ratio, we are above 20 decibels, which is good. It tells us that the original and the interpolated frame are of roughly the same quality. And we are 95% confident about that. And then root mean squared error, really what we want to look for here is that it's not a wide interval, because that tells us that the process could be inconsistent. And I'd say that in this case, it wasn't too inconsistent. For the standard deviation, since we have our measure of center and measure of spread, we want to look for low standard deviations because that tells us the interpolation process was consistent when it produced results. So if we have a really large standard deviation or a really large confidence interval for that, it tells us that our upsampling or our interpolation process was inconsistent. So it wasn't reliable in producing good results. For the upsampling metrics, this is where we look at the resolution upsampling phase, generate our validation data sets for it, and we compute things like structural similarity, multi-scale structural similarity. You can see that there was a huge improvement over the interpolation metrics. So between the upsampled and the original frames, they were strongly alike, very strongly alike, and we're 95% confident about that. For the PSNR, and I just want to make sure I really talk about this. For the upsampling metrics, we want to look for small PSNR values. The reason why is because the original image is of lower quality than the upsampled image. So we hope to see that the original image is of bad quality compared to the upsampled image, which should be better. So we want to look for PSNR values that are below 20 decibels for the upsampling metrics, because that tells us that our upsampled image is a whole lot better than the original image. And then here's this one too. Looking at another example, you can see that the edges are sharpened. Some of the background noise has been blurred over. Again, it's because of the bilateral filtering. The median filter smooths out the artifacts and the noise. And also the colors have been enhanced, so it doesn't look as dull. And the metrics for this one were exceptional. I was really surprised when I saw this. Structural similarity, multi-scale structural similarity, really small confidence intervals. They tell us that we are 95% confident that these are strongly alike, which they look like. The PSNR value for interpolation is well above 30 decibels. It tells us that the quality is indistinguishable between interpolated and original frames. And the root mean squared error is very small. It's close to 0, which is what we want to see. There was minimal noise between the estimated and true. For the upsampling metrics, the same story. The two frames, the upsampled and the original, were structurally alike. That's what we want to see. The PSNR was small. Again, that's what we want to see because the original frame is lower quality than the upsampled. So we are 95% confident that the true PSNR value is below 20 decibels. So that's a great result to target. And the root mean squared error is pretty high because if we look at these images, we really changed the pixel values when it came to saturation and brightness. So a high root mean squared error is going to be expected. We'll take a look at this one. This is a video game application. So on the right side or the left side are the original frames. The right side are the upsampled and enhanced frames. And this was actually recorded on a PS4. It's an in-game cutscene. And you can see here for the interpolation metrics, structural similarity, multi-scale structural similarity. We're confident that the two interpolated and original frames are very strongly alike. The quality between the original and interpolated frames is strong. So that's a great result we like to see. And a small root mean squared error. For upsampling, same story, structurally alike. The thing that changes is that our PSNR value is above 20 decibels. So for upsampling, what that indicates is that the original and the upsampled frames, there wasn't much improvement between them, at least not from that metric. So the quality between the original and the upsampled are roughly alike. And that's how we can interpret that PSNR value for upset. Now turning to historical footage. So I actually found this, I was just searching for some historical footage on YouTube. This was from Alvarado Road. There was this guy, he drove all across San Diego and just took these photos of streets, of people, of cars, and just had it archived.
This is Google Maps before Google Maps. Yeah.
And one of the places I found, he actually started at San Diego State. You can see it kind of here. Here's the 8, and he just kind of drove down Alvarado Road. Well, on the left side, those are the original frames that he had. On the right side, this is the result from the upsampling process. So you can see that the cars, the edges of cars in particular, are kind of smoothed out. They're sharper. You can see some of the finer details in the background that were covered up in the original image. That's the nice thing about the Lanczos kernel, is it makes those finer details more apparent to see, especially when it comes to text. So Alvarado Road, what he marked it as, becomes a whole lot more legible in the upsampled frame because the Lanczos kernel works perfectly with text or any type of writing. It brings it out. It makes it more visible to the eye. So for the interpolation metrics, the frames between the interpolated and the observed frames are structurally alike. The PSNR value has a very wide confidence interval. And again, we're looking at historical footage. There's some frames that are going to be more damaged than other frames. So when it comes to looking at the quality of interpolated and observed frames, there's going to be a lot of variability there. And that's reflected in this wide confidence interval, especially for PSNR values that are measured on the logarithmic scale. That's a pretty massive change in quality. Same for upsampling, really good process. Here's the last piece of historical footage. This is looking at Otay Mesa Road. You can see here the colors are brought out. The color depth is enhanced. Some of the things in the background are made sharper. And again, same story. Really good interpolation metrics, especially PSNR values. We're 95% confident that the true median PSNR value is somewhere between 41 and 51 decibels. That is very good quality. And this is for historical footage too. So this is including damaged frames or things that may not look as well. And this is for the upsampling phase. Again, really good metrics. The true median PSNR value is likely below 20 decibels. It tells us that the upsampled frames were of higher quality than the original frames, and we're 95% confident about that. And pretty low variability when we look at the standard deviation. So the results for the historical footage were actually really good for these two videos. All right. I was going to show a live demo of the video remastering program. I'm not sure how much time we have, but I'm happy to answer any questions, or I can show the demo too, if you want.
I think the demo will be good.
Great.
Very good ending. Presentation.
All right.
Can we remaster when the slides are on?
All right.
What
So
happened?
this is the Python program for debugging, creating it. I use the PyCharm interactive development. It's a nice IDE that kind of simplifies things and keeps everything in a graphical user interface. So these are all the packages that we talked about, all the dependencies that were used in the remastering program. Now, when it came to the program itself, I created 3 classes. The first class is clip creation. And what this does is this takes the clip, sets up the image database, and pretty much prepares everything for the frame extraction, frame operation processes. So this is like the setup phase. Going down here to the next class, we have the frame operations class. This is where extraction, interpolation, validation testing, all those methods are contained inside this class. That's where parallel processing is built into. So for parallel processing in Python, we'll take a look at one class here. This one right here. when we're generating interpolation metrics. So you can see in this one single line of code, we can specify how many CPUs we want our code to run. And I pretty much allowed you to customize that in the remastering program. I used a default of 4 out of 8 CPUs, so half of them. And then this is turning a Python method into a parallel processing method. I'll highlight this for people on the Zoom to see. This code right here. And how do we do it? Well, we map it. So we have to make sure that we have all these things set up, because if we don't, we can't do parallel processing. That's why that clip creation class is so important, because it sets up things for parallel processing. It maps them. And then finally, the last class going down here is the video stitching class. So what this does is from our image database, right, that we created, is it's going to take those interpolated, those upsampled frames, combine them into one directory. And then what it does is it reads those frames back into Python, stitches them together, and it makes a video. And it does all of this without going to a third-party, video creation program or software. Going down here, we'll just run this each clip at a time. So what we do is we create an instance of the clip we want to use. So we make a call to the clip creation class. We specify the file directory, right, where that file is stored, specify the output directory, where we want the image database to be made, what the video name is, and it's an MP4 file, and also the minimum seconds and the maximum seconds, unless you want to use the whole video or if you want a specific clip. So what we're going to do here is we're going to take a 10-second clip and we're going to create an instance of it in Python. Down here in this part, this is also part of the clip creation class. This is all the metadata that we want to specify. So I'll highlight this, actually leave it unhighlighted. What we want to do is we want to perform linear interpolation. That's just a Boolean, so it takes true or false. You can also specify if you want SVD interpolation. So maybe you want to generate some bad frames for deep learning, train your model. Well, you can use that to create SVD interpolated frames just by setting it to true or false. But we're going to use linear interpolation. You can also adjust the settings or the parameters of the upsampling process. So what's the saturation? What's the overall sharpness? The edge sharpness. And the higher values these are, the more extreme the effect is going to be. You can also change the contrast, the brightness, how much color depth you want. That's called the unsharp parameter. And by bringing it up to 0.62, you usually want to keep it between 0 and 1. I found that 0.6 is a nice compromise because it keeps the original colors, but it also enhances darker colors. So that's just from testing. You can change the upscaling factor. So you can actually upscale to a certain height and to a certain width. We're just going to upscale the original video by a factor of 3 for the height and width. And for the validation data set, we're going to use a sample of 50 frames. And since it's a stratified sample, you can change how many groups are inside your video. I just use a default of 3. So we have a beginning, middle, and end group to take samples from. All right, so we'll run that. Let me open up the file where this is. And we're actually going to see the image database being made in real time. So it's going to be created here. I have an external SSD drive. We're just going to store it on that. We'll run this line of code here. Let it get everything set up. And here it is. So this is our image database. We'll take a look at it extracting frames. So from this 10-second clip, there were 300 frames. All right. So it was a 30 frame per second video. We took a 10-second clip. 30 times 10 is 300. So we have 300 frames that we're actually seeing in this 10-second clip. All of those frames are stored in here, inside the original frame directory. So now that we've extracted all the frames, let's create some validation data sets from it. So I'll just comment this line of code out. Let's run some upsampling metrics. And you can see here in the upsampling metrics, you can specify the confidence level. It's set to 95% by default, but you can change that to reflect whatever confidence you want. And also the number of CPUs for parallel processing. I'd rather not run 4 CPUs just because we're running Zoom 2 and I don't want my computer to crash. So we'll just do 3 CPUs and hope for the best.
I think you're pretty bold to do this on the fly.
I tested it out last night, but
Right.
all right, it looks like it is working. So we have a sample size of 50. We're actually going to generate 51 frames because 50 is a minimum sample size. We have 3 groups. So we have 17 frames per group to get 51 frames. That's 51 divided by 3. So we just round up. And you can see that with parallel processing, instead of 1 frame being upsampled at a time, when this generates, should generate pretty soon. You have 3 frames being created at once simultaneously. And that's because we pushed it to each CPU we've designated. So again, if you have a lot of CPUs or if you have the power to purchase a lot of resources, you can scale this program to make it even faster, even more efficient, just by specifying the number of CPUs. Are there any questions while we're waiting for this? Because it's got to hit 51 frames.
Well, that's okay. That's
And then we'll see 10 seconds worth.
Yes.
yeah.
Oh, good, we want to play hours or
Yes.
Spider-Man movie.
Questions from audience?
Would a supercomputer speed this up tremendously?
Tremendously. It would depend on how many CPUs that supercomputer has. You can have a really good processor, but since it's running on CPU, it is CPU dependent. You can also adjust the parallel processing to get it away from CPUs. So let's say you have several computers in a distributed setup. Well, then you can distribute a task to a computer or to their CPUs. Hypothetically. I haven't tried that, but I'm pretty sure you can do that with the Pathos module.
M.Sc social distribution, where you have networks of computers, people donate their computer
Right.
off hours and they just leverage that and for free.
Mhm.
We're gonna have citizens,
Yeah.
whatever. Citizens upscaling.
They'll probably want a piece of that pie though.
Are there any?
I know that SPD was your idea.
Yes.
And, did you ever try it on something that was Spirit Aspect?
Oh, that's right. So I did try it. And I actually tried, instead of doing the SVD all at once, I actually tried to do it on segments of a frame. So I tried to conduct SVD on these little square segments inside the original image, and it did not produce a good result. It needs all that information to properly reconstruct the frame. So if you try to partition the original frame into several sub matrices and perform SVD on those sub matrices, it's missing out on the overall information. And
What
you're,
if you just had split?
then it's equivalent to principal components analysis.
Yeah, I would imagine if you're gonna use it on segments, you'll need to do some kind of a segmentation, like on
Yes.
something that's the same image.
Yep.
And probably, and it's probably not,
Yes,
but, yeah, it's a great idea. If it would.
yeah. Are there any questions on the Zoom at all too?
Yeah, I'm wondering why use a upsampling matrix and interpolation matrix. The our M.Sc is so different. Seems a huge difference for our M.Sc. What's happening on that?
So since root mean squared error is a pretty rudimentary measure, it doesn't use a moving window. It doesn't take into account neighboring pixels. It just looks at the average difference between 2 frames. So if we're changing things like the saturation or the brightness of 2 images, we're drastically changing pixel values. So that's going to be reflected in the root mean squared error, which is going to have those really inflated values. It's also the noise component of the PSNR calculation.
Also, when you mentioned that the structural similarity index, but for visual and the reality is so different, sometimes so different.
Yes.
I think one reason is that your global structural similarity index uses the average for the whole pixels, but maybe some of those are unimportant or boundary pixels. They may not contribute much, but they are very similar. But main characters of that picture of that frame, this is huge difference. But because the weight is very, they use equal weight on that. That may be the reason that distort the when you visualize and when you calculate the measures, they are so different. Maybe you want to check it.
Yeah, that's a great point. So when we're taking the average of all those structural similarity values, remember, there's a sim value for every single pixel. We just take the average of them all. Now, if we look at the sim value for a border, right, that lies on the border of an image, that sim value is padded with zeros when we calculate it. So that's going to be an inflated value that's close to 1, because obviously those two things are going to be strongly like. So when it comes to taking the average of it, we're also taking those really high sim values, which could be causing some inflated metrics. Perhaps something like median or a more robust measure of center might mitigate that effect. But that is a good point.
Yeah, I have a question on the bootstrapping.
Yes,
I don't know if this makes any difference, but there is an order to your frames.
yes,
So when you're doing the stratified, you have the beginning, middle, and the end.
Mhm.
And times, so you're sampling with replacement,
yes,
and so things have to be independent, but there's some structure in your video,
right,
and you're kind of losing that. So I don't think you're inflating the percentile intervals much, but in time series, there's something called a stationary bootstrap, where you go and get sort of chunks of data to put it together to keep the autocorrelation structure.
oh, okay,
And it's sort of an idea where you would go out and get a random pixel, and with a certain probability, you go take the next one.
oh,
And
okay,
in another probability, you go out and get another one.
Right.
So you can build in some correlation structure. So I'm worried about the idea that you have, when you do sampling with replacement
Right.
in a sample, about 2/3 are in sample and 1/3 is out. So there's a lot of repetitive
right,
frames, and I was trying to do what
Yep.
would happen if you had many frames that were the same. And you did your algorithm and used that for part of your stationary bootstrap, or your bootstrap.
right,
Whether that is good. I mean, if you do your
Yeah.
whole
I
thing.
was actually gonna inquire
Yeah.
if you thought about using a systematic sample instead
Yeah.
of stratified.
Yeah, well,
did-
that's why there's this idea, if you want to do
Right.
beginning, whatever. So I don't necessarily think you need to have long stretches of the same bootstrap, because that's, not, you're only, when you're doing your upside and down sampling, you're only doing, in one in between. But you want to make sure that that's representative of what you're doing, instead of having many,
right.
frames that are the same, and you're doing your thing,
Exactly.
so the same
Yeah.
idea, so.
That's a good point.
Yeah.
And to get back to what Kristin mentioned with the systematic sample, I actually did try that first. The reason why I abandoned that approach is because when I systematically sampled frames, I was targeting all the frames that didn't have abrupt scene changes. And this was just by random chance. So when I did the stratified sample, is I tried to divvy it up into those 3 main groups. And in that way, I'm taking a simple random sample. There is no system behind it, but you are losing some of that autocorrelation.
Yeah, so maybe something.
A hybrid.
The hybrid,
Yeah.
so you go out some that are the same, but they're gonna be different.
Right.
And represent the same, same
Right.
frame selection.
That's a good point. Yeah, taking a hybrid approach between a systematic sample and stratified sample.
Or build in that short correlation structure,
Right.
so you get a few chunks together.
Yeah,
So,
it's a great point. All right.
Okay, got it? Okay, all the frames,
Yes, so here we have our 51 frames that are generated.
show the movie time.
Yeah. I just want to show, so this is frame 37. This is our upsampled frame. Let's take a look at the original frame for comparison. So since we name them in this way, we can just quickly see and match them based on their names to see the increases visually from the original and the upsampled frame. Oops, let me drag this down. Yeah, that's good enough. So here's the original. Here is the upsampled. You can see that the colors are enhanced. The features are a little bit sharper, especially in the background. So that's just one example of the comparison. Looking at some metrics, we'll go to the frame quality metrics. So what the program also does too is it spits out an Excel file measuring or containing all of these metrics. We did upsampling, also has histograms too that I made. And you can see that for these 51 frames, I know it's pretty small to see up on the board, but we start at 0.945 or about for our structural similarity. Then we go all the way up to 0.97. So high structural similarity. Again, it's taking the average, so those inflated values have to be taken into account. For peak signal to noise ratios, most of them were below 20 decibels, which is great for the upsampling process because it tells us that our upsampled frames were higher quality than the original. And for the bootstrapping, we'll open up this Excel file. Our median point estimates for each one of these metrics are recorded here. Now, again, with the bootstrapping approach, we took 1,000 samples with replacement using the original sample size of 51 frames. And what we did was we took the median value for each one of these estimates. Same thing with standard deviation. Here's our standard deviation estimates, right in this column, column F. So you can see that there was very little variability in the upsampling process. Our standard deviations were pretty small. And also in columns D and E, that represents our lower and upper confidence interval boundaries. And in columns H and I, that is our lower and upper standard deviation confidence interval boundaries. So it produces this for every validation test. Let's save that. And then to get to the video, we'll just skip past this part. Do this. Let's upsample the original, perform interpolation. And we're going to make a video out of it. All right. So we'll let this run. I'll answer some more questions, and then we'll see the 10-second remastered video after that.
I have a question about structural similarity values. So they go from -1 to 1, but it said -1's not included in that range. Is there a reason why images can't be like exactly opposite?
It's like a good question because when I did research on it, I used the structural similarity that's built into TensorFlow. And when I was doing some research on the documentation behind it, for whatever reason, it didn't include -1. It did include +1. So I'm not sure if it's something with their calculation. I didn't really get a definitive answer on that. I'm just pretty much using what TensorFlow's documentation said. But that interpretation still applies if it's close to -1, it's negatively similar, close to +1, they're very alike, and 0, there's no similarity. Yes.
So you created something that's quick and easy and produces good results, but you have alluded to the fact that sometimes people might want to do more.
Exactly.
Do you have guidelines for when, or it's just a visual thing where you look at it and you're like, I want to do better, or
Right.
based on the metrics?
I'd say that it's a combination of visual subjectivity and also how you interpret the metrics. So depending on if you're happy with how the frames look visually, then you can use the metrics to see, all right, can I improve on this? Can I improve the PSNR value to something above 30 decibels? Can I target that in a deep learning model? And actually, Anna and I were doing some research on neural networks too right now. And there are some neat ones out there for generating entirely new data from existing data that can be used. One of them is a generative adversarial network. And that's a nice way of pretty much training your model on the same data set that you put into it to try and create images that trick the model into thinking that they're the real images. So it has a discriminator and a generator. So that's one approach you can use. And you can use those bootstrap metrics to kind of like set a baseline. Can your model improve from that point? Does that answer your question, Kristin? Thank
Yeah,
you.
and suppose
Yes.
I'm an impressionistic person, and
Yeah.
I just want to have everything smooth and,
Yeah.
you know, that kind of thing, then there's guidance for where I should put the parameters in order
Yep.
to make
Yeah.
my 10-second video.
Exactly.
Nice.
Yeah, that was kind of the framework for how I wanted to do this too, is I didn't want there to just be one standard
Yeah.
way of doing it. I wanted the user to be able to customize it to their preferences to see if they can get a better video that fits their style, their tastes, just by changing some of these parameters in the program. All right, so here's all of the upsampled frames. So there were 300 frames total. If you look in the bottom left corner, we're at 270 frames. Looks like it's still generating them. You're gonna see a few of them pop up again. Anytime now.
I got one question I had,
Yes.
I forgot what was the end of our discussion. There, in the methodology we do this, called post difference, and in the self-driving monitoring system
Right.
also. So instead of processing original data RGB,
Mhm.
so you process the difference
Yes.
of the RGB of this frame to the previous frame. The advantage of that in common sense is that, so we understand that you ask it, well, how many degrees today? You probably do not know, but one thing you do know, but today is hotter than yesterday. So this hotter than yesterday, that's the sharper signal.
Mhm.
So instead of using, say, how many degrees today, we use, say, today is hotter. So they, well, today might be, no, look like today's 3 degrees hotter than yesterday. That is so we use that called first difference data.
Yeah.
To do the processing. We discussed this, I forgot where we are.
Yeah, so first differencing when it comes to this, that's a nice time series approach for handling sequential data in a video. This kind of touches on what Barbara and Kristin mentioned as well with keeping the autocorrelation intact. I did not do first differencing on this. What I did is I tried to keep the frames in their order, but I tried to treat them as identically distributed and independent. So I did not do linear first differencing or second differencing. That could be an approach to doing this as well. And I think that would be a very valid approach.
Okay, so we have not, well, we talked about it once, but I forgot where we were. So yes, the self-driving system, they are using this to make they make the signal sharper because the self-driving system they need. Number one is a sharp signal. Number two, fast. So what is fast? Because each frame, as you know, much of that is from previous frame.
Right.
So it allows you to do faster processing,
Mhm.
and then after you have done the processing, you add back, you recover those the original.
You know, when you're saying that right now, I actually think you're describing the linear interpolation process. Because what you're doing is you're actually Wow, when I thought about that, you actually just described the linear interpolation. You take the two observed frames, you find the difference between them, just the first order difference, and you add that difference to the first frame to produce the interpolated frame. So it actually does use first order differencing. I just wasn't connecting the terminology there for you.
Yeah, we discussed this. I remember,
Yeah.
but I forgot exactly what have you done.
Yeah.
That's kind of thing we want to enhance so that the signal will be sharper.
Right, right. That's something that we talked about too. With the interpolated images as a whole, they will be blurrier than the original images. You lose some of that spatial variance from the interpolation process. The hope is that when you upsample it and you run those convolutions, you can bring some of that sharpness back while also reducing the noise that came from the interpolation process. And that does happen in some cases. Other cases, it may not happen. It depends on the quality of the video, how the video was recorded, things like that.
So we do research grandma can understand.
Exactly.
If grandma thinks it's okay, it should be okay, right? So grandma says, this is a smart idea. It is a smart idea.
Are there any questions on the Zoom at all? All right, then I will show the remastered video. So just to put it in
Away from the-
perspective, here's the original video. We'll show that one first.
Away from the fact that I found him crazy. I am not crazy. I know he swapped those numbers. I knew it was 1216. One after Magna Carta, as if I could ever make such a mistake. Never. Never.
So you can see that the frame rate, this is recorded at 30 frames per second. A little choppy when it comes to moving it. That's just how the frame rate is. You're only seeing 30 frames played for each second. This is the end product, the remastered video.
Away from the fact that I found him crazy.
A little bit smoother when it comes to their movements, especially when there's
I'm
not
not
drastic
crazy.
changes.
I know he swapped those numbers. I knew it was 1216. One after Magna Carta, as if I could ever make such a mistake. Never. Never. I just couldn't prove it. He covered his tracks. He got that idiot.
And you can see in this case, we actually probably over sharpened the video to begin with, because you can see that there's some artifacts on the edges. But again, these are all parameters you can change and customize to your liking. You can adjust the saturation, the brightness, how much sharpening is done. But this is the end result. So we have an upsampled resolution, 4K resolution, a doubled frame rate of 60 frames per second. And you can actually verify that by looking at the properties of the video. Go to details. So it's really small to see, but we have a frame width of 3840 pixels, a height of 2160 pixels. And if we look down here at the frame rate, well, we're targeting 60 frames per second. And this is after the results of the interpolation and the upsampling process.
Much larger is the revised.
Oh, good question. Let's take a look. So the size of the video file for the remastered one is 137 megabytes. And also bring up something I talked about or wrote about in thesis. The preset I use to stitch these frames together in MoviePy is set to ultra fast. So it's not compressing the video. Instead, it's sacrificing compression for speed. Because if you try to stitch together 20,000 frames, that can be very time consuming. So there's an optimization where you're not compressing the video, but you're making it faster to make or output. So the original video was only 12 megabytes. And the remastered video, uncompressed, is 137 megabytes. So it's a pretty significant increase.
That was part of 10 seconds.
This one was actually looking at it. For this
Away from the fact
example,
that I found him.
this was actually a minute and 13 seconds. So we looked at the same clip, just a different example, because it was taking too long. But yeah, that is a minute and 13-second video. So it can accept pretty decent clip sizes. You might want to compress it after the fact, or also change the preset from ultra fast to something that does compress it. But those are all customizable as well.
Okay, very good.
Great.
Thank you.
All right.
Very good, thank you. More questions?
One question.
Yeah.
A repurposing, expansion of the idea, the audio.
Oh, that's a good point. When it comes to reconstructing audio, we actually talked about this in the proposal defense too a little bit. A lot of these upsampling techniques, since we're looking at, things in 2 dimensions with videos, we just have to repurpose them to 1 dimension for audio. And that's very easy to do. It would take some augmentations, and also, there is no such thing as brightness or saturation in audio, but there are equivalent filters you can use, convolutions you can run to try to enhance the audio. So it could be extended to that with some modifications.
I know there's some organizations that do that.
Yeah,
The, car backfires, they try to remove all those noise
right.
to try to get to a more clarity with the audio. They
Right,
did that with the JFK assassination, because they thought there might have been a fourth one.
Yeah.
Because, but they found out that, because they were trying to determine,
right.
the grassy knoll.
Uh-huh. Yeah, that's a good point. This could be extended to covering audio as well. As it is, I'm just using the existing audio from the original file. There are no enhancements made to the audio. So the audio that's there is the audio that gets carried over to the remastered video.
Okay, any other, no, okay, without further question, I would suggest that the committee members stay in the room, we'll discuss about your evaluation.
Great.
And you may bring your grandma and parents out, wait there a
Sure.
little bit, don't go very far, we will invite you to come in.
All right.
And,
Awesome.
just stay there outside.
All right. Thank you everyone for attending.
Come back, we will come back for the.
Yeah.